Anker has just announced a new chip called Thus, claiming it delivers 150 times more AI compute for earbuds. This sounds like a revolution in consumer audio, but the real stakes here are far higher than just better noise cancellation. If you are a robotics engineer, this claim is a trap that could lead you down a path of hardware selection that fails when it matters most. By the end of this explanation, you will understand exactly why a raw compute metric that works for listening to music is completely useless for a robot trying to navigate a chaotic room. The marketing behind the Thus chip relies on a specific architectural approach called compute in memory. To understand why this is exciting yet dangerous for robotics, you must first understand what compute in memory actually does. Traditional processors move data back and forth between the processor and memory thousands of times for every calculation. This movement consumes massive amounts of energy and creates a bottleneck known as the von Neumann bottleneck. Compute in memory eliminates this by performing calculations directly inside the memory array itself. Theoretically, this should allow for incredible density and speed because you are no longer waiting for data to travel across a bus. Research papers on this technology, such as those analyzing NeuroSim and UPMEM architectures, confirm that these systems can achieve energy efficiencies exceeding 100 TOPS per watt in simulations. They show that for certain memory-bound workloads, the speed gains are real and the power savings are significant. However, these studies almost exclusively focus on high-performance computing environments or general-purpose memory tasks. They do not account for the extreme constraints of a device the size of an earbud, nor do they address the specific demands of robotic autonomy. Here is the thing that the marketing materials do not tell you. The 150 times figure is likely a theoretical maximum derived from comparing a narrow audio task against a legacy digital signal processor. It assumes ideal conditions where the chip can run at peak frequency without overheating. In the real world, an earbud has a millimeter-scale form factor with almost no ability to dissipate heat. When you push a chip to 150 times its previous performance, you generate a tremendous amount of thermal energy. Without active cooling fans or large heat sinks, the chip must throttle itself to survive. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This thermal throttling creates a fundamental problem for robotics. In a consumer audio device, a slight drop in processing speed might cause a momentary glitch in noise cancellation. In a robot, a drop in processing speed can be catastrophic. Robotic autonomy requires sub-millisecond deterministic latency. The robot must perceive its environment, calculate a trajectory, and adjust its motors within a strict time window. If the chip overheats and the processing speed drops, the control loop breaks. The robot might stutter, drift, or worse, collide with an obstacle. The 150 times gain is irrelevant if the thermal ceiling forces the system to operate at 10% of that speed for most of the time. Another critical gap lies in the precision of the calculations required for complex tasks. Robotics relies heavily on simultaneous localization and mapping, often called SLAM, and perception stacks that use vision transformers. These algorithms demand high-precision floating-point arithmetic, typically in FP32 or FP116 formats. Current compute-in-memory architectures, particularly analog implementations, struggle with this level of precision. They are prone to noise and variability, which makes them better suited for the lower-precision integer arithmetic used in speech recognition or simple audio filtering. Because of this precision limitation, a robot using a chip like Thus would be forced to rely on heavily quantized models. You would have to compress your neural networks to INT8 or lower to fit the hardware. While this saves space and power, it degrades the accuracy of the perception system. In a dynamic environment with changing light, moving objects, or slippery surfaces, a quantized model might fail to recognize a hazard that a standard high-precision model would catch. The theoretical compute density gain is traded for a loss in the fidelity of the robot's understanding of the world. Furthermore, the energy cost of the surrounding system often dominates the chip's efficiency gains. Even if the compute-in-memory unit is efficient, the rest of the system must still handle sensor synchronization, control theory calculations, and data conversion. The energy cost of moving data between the sensor array and the memory, and then converting that data for the specialized compute unit, remains a significant burden. In a mobile robot, the battery is the primary constraint. If the chip consumes power to maintain high density but forces the battery to drain faster due to the overhead of memory I/O, you have not solved the autonomy problem. You have just moved the bottleneck from the processor to the power supply. There is also the issue of what we call dark silicon. The thus chip is specialized for specific audio workloads. It is not a general-purpose accelerator that can be dynamically reconfigured for the diverse and unpredictable tasks of a robot. A robot might need to process visual data for navigation, then switch to processing audio for voice commands, then switch to analyzing sensor fusion data for balance. A specialized chip like thus cannot adapt to these shifting workloads. It is optimized for one thing, and when the robot needs to do something else, the chip becomes a bottleneck. The lack of flexibility means the hardware cannot handle the heterogeneous processing required for true autonomy. The real-world benchmarks for consumer audio chips focus on single-task metrics like call clarity or background noise reduction. These are linear, predictable tasks. Robotic autonomy requires heterogeneous processing, where the system must handle multiple streams of data simultaneously. The lack of specialized hardware for non-AI tasks, such as sensor synchronization and control theory, creates a system-level latency bottleneck. No single AI accelerator, no matter how dense, can solve this without a holistic system design that accounts for thermal, power, and latency constraints. The 150 times claim is a theoretical maximum that ignores the dark silicon problem and the architectural mismatch between consumer audio and industrial robotics. It is a metric that works on paper but fails in the field. Until there is empirical data demonstrating sustained performance under strict thermal ceilings and variable loads, this claim remains an unvalidated theoretical maximum rather than a practical engineering reality. For the robotics engineer, the lesson is clear. Do not be seduced by raw compute numbers. Look at the thermal budget, the precision requirements, and the latency guarantees. Those are the metrics that determine whether a robot can actually move through the world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.